Hello everyone, this is my Lab 2 presentation on the motion of a falling object. The general overview of this lab was to identify an object's motion from rest given non-constant forces. The methods utilized in this lab was first an experimental observation through tracker, and later on the use of two computational models, one with only gravity and the other with gravitational as well as drag force. The general results was that the computational model, including both drag force and the force of gravity, was much more similar to that of the experimental model. And the major principles starts with Newton's second law. To dive a little bit deeper on the fundamental principles, as I've said, Newton's second law shows up in this lab in the form of the momentum equation, as well as the general mass times acceleration. In addition, there was also the gravitational force formula, as well as the drag force formula. Finally, the inclusion of the velocity and positional update formula was also needed, especially in the computational sides. For the observed data, the system was just an open box dropped from a specific height, and from tracker, the data points were determined and graphed, and as we can see, this was a downward facing curve, which meant that velocity was non-constant, acceleration was non-constant, therefore the net force was non-constant. On the computational data side, to first discuss only gravity, there was then no need for the proportionality constant, which is why B was 0. The ball's mass, or the box's mass, was identified, and inside the while loop, the net force only concerned the gravitational formula because gravity was quote-unquote the only force acting on this data set. In addition, the velocity and positional update formulas were also included to calculate the ball's next, or the box's next point. On the drag force computational data side, the proportionality constant did need to be included, and to identify the constant I chose, it was through trial and error to match the data set's final position as closely as I could with the experimental data's final position. Inside the while loop, not only was the force of gravity included, but the drag force was also included, utilizing the formula, the negative proportionality constant multiplied by the speed squared in the negative y direction. The net force then was the accumulation of both the gravitational and drag force, and the rest is pretty similar to the gravitational computational data code. In the graph, 3 lines were drawn. Yellow identified only the gravitational force, red identified both the drag force and gravity, and blue was the experimental data set. As you can see, when gravity was the only acting factor, the position of the box would have reached a much farther distance. But with drag force correctly calibrated, the red line was much more closely related to the blue line, which meant that there was a specific drag force or a non-constant net force. For the first question on whether or not terminal velocity is reached in one of the models, it is reached in the computational model, including both gravity and drag force. As we can see on the velocity versus time graph that the drag force model has, velocity is slowly approaching that of a 0 slope. If the slope of the velocity graph is 0, then we know that the change in acceleration, or the acceleration at that time, is also 0. Therefore, the net force is 0, which matches the description of terminal velocity, since when terminal velocity is reached, there is an exact balance on the force of gravity and drag force. The second question on a discussion of whether or not initial velocity affects terminal velocity, comparing the two graphical representations, we could see that it does not, since the final velocity approached is still very much the same in both models. What initial velocity does have an effect on, though, is the time at which terminal velocity is reached. Thank you very much.